Welcome. We are in Chapter 4, Exploring Numerical Data. The focus of this lesson will be on outliers and box plots. There are three things that you all should be able to do by the end of this lesson. Number one, you should be able to calculate the range and interquartile range of a data set. You should be able to identify any outliers that exist within a data set. And then you should be able to compare two different distributions using shape, outlier, center, and spread. So we left off last time just, very briefly addressing the idea of how large or small values can have a big impact on our mean and range. Okay, so one way to think about that, if we were to think about the mean salary of a high school class, okay, let's take our class in Rockford, okay, my normal classroom, and let's say we were to figure out what the average salary was and then what the range of the salaries were of the students. For the most part, they'd be relatively close. The mean would be a relatively reasonable number. But now let's all of a sudden say Adam Sandler. Okay, it turns out he's one class short and has to go back to high school. Oh, gee, maybe it's Billy. Anyway, so, okay, we've got to look at that. Now all of a sudden he's in our class because our class is what he needs. Well, how is his multi-million-dollar salary going to affect our little itty-bitty mean that's so small where it is? Right? It's going to have a massive impact on it. Whereas the range, massive impact on it, right? Because now that top number is so much bigger. Now on the flip side, though, what happens if we think about our median, right? It's only going to shift over just a little bit, right? Our interquartile range isn't affected at all by numbers on the extreme one side or the other, right? It's only that middle half of the data, so it'll have very little impact at all on it. So when we look at outliers, okay, what exactly is it? Well, it's something that falls out of the normal pattern, okay? When you look at your data, when you have numbers that are just unusually high or unusually low, okay, those are considered outliers, okay? Because they're going to have a big effect on things like your mean and your range. So let's take a look. We're going to look at the Tennessee Titans versus the Baltimore Ravens 2020 NFL playoffs. Derrick Henry carried the ball. He carried the Titans to the win. Okay, he rushed 28 times, 195 yards. I mean, he just crushed it. Okay, so when we look at his dot plot of rushes, right, the yards per, or the individual rushing attempts, right, these are the number of yards he got in each one. Okay, so you can see the vast majority of this data, right, all falls under 10 yards. Okay, in fact, all but 3 of his carries fall somewhere between 0 and 9 yards. Okay, we have these other 3 points that are in the 20s for 2 of them and over 60 for this third one. Okay, those don't really appear to fit the rest of the pattern. In fact, when you look here, right, our mean is 7, right, but got pulled up a bunch from our median, which is only 3, right? So you can see where those couple of big rushes had a really big impact on the mean, but not a very big impact on the median at all. So, okay, one of the things that we talk about is if a measure of center or spread is resilient or not resilient. Okay, resistant. Okay, it is resistant, okay, if it isn't influenced by outliers. Okay, so the two that aren't influenced by outliers are the median and the interquartile range. Okay, they're resistant to outliers. Whereas our mean and our range are not resistant to outliers because outliers will have a very large impact on those numbers. So as a rule of thumb, okay, for an observation to be considered an outlier, okay, it has to lie 1.5 interquartile ranges below the first quartile or above the third quartile. So here we have it written out. Hopefully this will be a little more clear for you. So if you just take 1.5 times whatever your interquartile range is, you subtract that from Q1, that'll tell you what the bottom limit is. And then if you take that same 1.5 times your interquartile range, you add it to your third quartile, that'll tell you what your upper limit is. So let's take a look at Derrick Henry's 28 rushing attempts. Okay, here they are in order. I laid them all out, 0, 0, 1, 1, 1, 1, right? So you can see, right, it's very, very consistent all the way up until you get to those last 3. Not going to lie, this kind of reminds me a little bit of what Barry Sanders used to do for the Detroit Lions back in the 90s. So if we count over, okay, there are 28, so we count over and we get 14 and 15 because those would be our two middle numbers. Okay, it's 3 and 3. Well, if we add those two together and divide by 2, that gives us Q2, or a median of 3. That now splits our data into two separate groups. So if we go within those groups and we find the median of each one of those groups, okay, on the bottom end, that gives us our Q1, which is 1 plus 1 divided by 2, which is just 1. And on the top end, that gives us 5 plus 6, which divided by 2 gives us 5.5. So now that I have my first quartile and I have my third quartile, that means I can find my IQR, or inner quartile range. So if you remember correctly, you take Q3, subtract Q1 from it. So 5.5 minus 1 gives us that 4.5. So our inner quartile range is 4.5. So now if I want to find that lower boundary, I need to do Q1 minus 1.5 times my inner quartile range. So that gives me 1 minus 1.5 times my 4.5. Make sure you use your order of operations to do the 1.5 times 4.5 first. And when you do that, you get that that's a negative 5.75. Well, when we look at his data points, he had 0 rushes that resulted in negative yardage. So clearly, right, there are no values below it. Therefore, there are no outliers on the lower end of the distribution. So now we need to do the same thing to look at the upper boundaries, right? So we're going to take Q3 and we have to add 1.5 times our inner quartile range up here. So again, that's 5.5 because that was our Q3 plus 1.5 times our 4.5. Again, remember, make sure you do the 1.5 times 4.5 first. And when you do that, you get 12.25. So this means any of these data points that fall outside of 12.25, that means they're too high. Okay, so when we look at this, right, we have 3 values that fall outside, which are the 3 that we predicted, right? Way back at the beginning of this example, we said the 23, the 27, and the 66 just seem so far out of the realm of the rest of the data. So we have those 3 values, right, as we've already said a couple times, that are just too high, okay? They're just way up there on that upper end. Okay, so what we can do, one of the ways that we can graphically show this data, or in chart form or whatnot, a plot, okay, that you guys, I think you guys have done these before, but if not, it'll be a great learning experience. Okay, is to graph the distribution, okay, in a box plot. Okay, you may have learned how to do these as a box and whisker plot back in like pre-algebra or algebra 1. We're just going to call them box plots. Okay, so it's the visual representation. We're going to look at the 5-number summary of the distribution of numerical values, okay? And those 5 values are your minimum value, your first quartile, your median or second quartile, your third quartile, and then the maximum value of the distribution. Now, steps to make a box plot. Okay, number 1, you're going to draw a central line, okay, on a number line for the first quartile to the third quartile. Okay, and then you're going to draw a vertical line to mark the median. You're going to draw a horizontal line that's called a whisker that extends the box out to the smallest and largest observations that are not outliers. And that's a key, okay? Outliers are dots. They are not drawn on. And don't worry, I'll show you an example of this here in a second, so don't get too confused on me. Okay, and then as I said, we're marking those outliers separately. Okay, so if we go back to that Derrick Henry example, okay, and we re-examine his rushing attempts, and let's look at that key data. Okay, so here we are again. Okay, we already looked at this. Our minimum was 0. Our maximum was 66. We figured out our 3 quartiles, Q1, Q2, and Q3 were 1, 3, and 4.5. And then we said the outliers were 23, 27, and 66. So when we draw this out, if this is our number line, okay, notice we have 0 to 70 on our number line. Okay, so if we drop lines at 0, 1, 3, 5.5, and then we remember, we don't go all the way to 66. We go to the largest one that is an outlier. So it's going to be at 9. Okay, this is what it looks like. Okay, so we have our line here, right? Our point for our smallest at 0. Okay, a line at 1. Okay, a line at 3. a line at 5.5, okay, and then another dot here at 9. Now, it appears as though there's two lines here. I don't know why it's showing that way. That should really only be one line breaking that data up. But now we have our outliers also. We have this 23, 27, and 66. So we just put points at 23, 27, and 66. So anytime you look at a box plot, as soon as you see dots, you automatically know that you have outliers. So when we're comparing distributions, okay, there are four different things that we have to address. We have to address the shape of the distribution, if there are any outliers in the distribution, where are the centers of the distribution, and what does the spread of the distribution look like. So if you're kind of wondering like, oh man, how am I going to remember these things? Just use the old acronym SOC, S-O-C, and then S. I know it's not spelled right, but you guys can do it, okay? So SOC, S-O-C-S. Okay, shape, outlier, center, and spread. Okay, so the shape of a distribution may be difficult to determine from a box plot. Okay, that's a little bit more difficult, right? So the way that we have to do it, because it's not super obvious right away, is we want to compare the distance from the median to the minimum and maximum values to see if it's skewed one way or the other, or if it's roughly symmetrical. If it's about the same distance in both directions, it'll be roughly symmetrical. Okay, you won't be able to tell if it's unimodal or if it's, bimodal or any of those types of things. So that's one thing that's one disadvantage of the box plot. So we're going to look at these box plots. Okay, these are AL and NL back from 2008. Okay, and they're on the same scale, so they're easier to see. So we're going to look at the four different things that we want to look at to determine, okay, what would be a good comparison of these two box plots. Okay, so our first one, all right, starts with the S, is shape. So as we look at the shape of these two, okay, as you look, right, the AL is the top one. Notice how it seems to be skewed to the left. Now, why is it that we'd say it's skewed to the left? Notice how this side is much smaller, right? So that part of the data is much more tightly bunched. Okay, so that's why we would say that it is skewed to the left, right? The left half of the distribution appears to be much more spread out. Whereas the NL seems roughly symmetrical. Okay, it seems about the same, roughly the same distance on both sides of this. The whisker on both sides, roughly the same size. So it's roughly symmetrical. Okay, up next we have our O for our outliers. Well, I don't see any dots, okay, on our box and whisker plots. So we're good there. Okay, up next we have our center. Well, clearly the American League center is quite a bit further along, right? This one is back here at like 740. This one's all the way up to almost 790. Okay, so it appears as though, right, the median for the AL is quite a bit higher. Okay, and then the spread, well, the AL looks like it is spread out further, right? There's a larger range, and because our box is bigger, there's a larger interquartile range than the NL. So as we looked at in the 2019, the same thing from the other day, right? The NL was more spread out, the AL was, and the NL is more consistent. It's closer together. Okay, so just remember, okay, those four things. Hopefully you learned a lot, and hopefully you're having a great day. Bye.